Hi, how are you doing?
I'm good, thanks. I'm with eSolutions. I'm just going to be checking on your live stream for a bit.
Yeah, cool.
About 10 minutes and then I'll head out.
Yep, awesome. Thanks for that. Alright, thanks guys. Alright. We're going to get started on time, everyone. So thank you very much for being a bit quiet. So just to introduce myself again, for those that weren't here last week, my name's Sean Gregory, co-teaching this unit with Steve Dubsky. And this is biomedical imaging and sensing. So just a little bit more about myself before we get on today's lecture material. So I do like to pick on people a little bit. So just to make sure you're all paying attention, I will be roaming around the room sometimes and getting you to answer some questions or give your thoughts. And it's a good way to encourage discussion on the topic as well. So I'm sorry if I pick on you, I'm not picking on anyone deliberately, but it's just to encourage discussion, so please pay attention. So today we're going to be talking about an introduction to sensing principles, and then next week, you're very lucky, you'll have a guest lecture from Professor Uli Steinzeifer. Today's is a little bit theoretical, unfortunately. It's going to be a little bit dry, but we'll try and make it as interesting as possible for you. And then in week 3, you will then have a more practical lecture on the applications of the theories that I'm teaching you today, talking about how we can use these sensing principles in actual biomedical applications and looking at some real-world sensors. So today we will learn the basics of, firstly, what is a sensor. We'll talk about some classifications of different sensors that we have. We'll look at a lot of performance characteristics. That's going to use up the majority of the lecture today. And then we'll also do some examples related to those performance characteristics at the end. So for those of you that were quite organised, you would have seen on the Moodle site that there's some pre-reading. The first bit was a National Instruments white paper on sensor terminology. So we'll be talking about those characteristics that they mentioned in that paper a little bit today and going into some more details. There was also a BMJ journal for sensors in medicine on there, which just briefly discusses the use of sensors in medicine and how important it is. It's an old article, so it's not as relevant as perhaps it could be, but it's still something interesting for you to read if you haven't done it yet. And then post-reading, for those that are very, very keen, there is a wonderful textbook called Introduction to Biomedical Engineering by Endel and Bronzino. You can get a copy of the whole textbook for free if you do a Google search online. So it's easy enough to find, and I think it's chapter 10 is about sensing, and there's also another chapter around that that's quite interesting as well. So feel free to have a read of that if you're just quite interested in this topic and you want to learn more. So first of all, we're going to start off with what is a sensor. So can anyone tell me what their definition of a sensor might be? Feel free to speak up, or I might have to pick on a couple of people.
Input.
Sorry? So it gives us an input? Yeah, anything else? Oh, someone's read the slides from last year? Oh, that's almost exactly what I have on the slides as one of the answers. So very, very good. Okay, so it essentially converts energy from one medium to another. I mean, there's a few definitions that we can apply here. So we could say that it's a device that detects or measures a physical property. A sensor conveys a form of energy, one form of energy to another, exactly how you said, which is why I thought you'd somehow gotten a copy of my slides. We can also say a sensor is a device which provides a usable output in response to a specified measurement. So essentially, a sensor is something that acquires a physical parameter and converts it to a signal that can be processed or used. Okay, so it's important that we are able to process or use it in the form that it's converted to. Whether that's electrical, optical, or mechanical, there's a bunch of different ways that we can do that. So then we have the question of why do we need biomedical sensors? I can think of a load of mechanical applications for these, and I'm in the biomedical field, so I can think of a lot of medical applications. But can some of you give me some examples of where you've encountered sensors, or someone you know, or you've seen sensors that have been used in a biomedical application? Sorry? Temperature? Yep. Sorry? Yep. Yep. So basically they can be used for a bunch of different measurements, whether it's blood or body temperature, or a whole bunch of different reasons. But essentially we have a few different primary goals with sensors. And the first thing is diagnosis. So sensors are really commonly used for diagnosis. You might have seen someone go to the doctor to get an ECG or an EKG, looking at their heart rhythms. We have a lot of even imaging which can be used for diagnosis as well, which Steve will go through later on in the unit. Blood pressures, things like this. So it gives clinicians information on what is wrong with the patient, or it tells the clinician that the patient is perfectly healthy. Then we use them for monitoring. So it's not just diagnosis, we use them quite extensively for monitoring. So this is particularly done in the hospital, but you can also get sensors for at-home monitoring as well. Some of you probably have smartwatches on at the moment that are detecting your heart rate. That's a sensor that's currently being used for monitoring. So it's very commonly used for this, whether it's at home or in the hospital. Another very interesting use of sensors is control. So there's a new generation of medical devices that's coming out now that are trying to sort of become one with the patient. So they're actually sensing what the patient is doing and then using that feedback to control the device. So the previous generation of medical devices, whatever was manufactured, whatever sat on the shelves was what you got. There was no way to change the device really, or no active feedback to change the device as you progress with your treatment. Whereas now devices are starting to use these sensors to actually become one and respond to you. So some examples are the modern generation of pacemakers. They no longer just work in sort of one rate or anything like that. They actually detect the impedance of the heart and then change the way that they perform based on what you're doing. And it's the same thing with also some glucose delivering tools and things like that. So the regulatory authorities around the world are now starting to understand that one-size-fits-all devices, medical devices, are not what we need. We need things that can actually adapt to what the patients need, not just individual patients, but individual patients in their day-to-day life. We need to be able to adapt that. So sensors are used then as an input to a control system to keep the device up to date. We also need them for preclinical evaluation, or also clinical evaluation. So when you're developing a sensor or developing a medical device, you would obviously use sensors to demonstrate the efficacy of the new device. So that might be in my application, I develop new artificial hearts. Now we need to know that they are delivering the right blood pressures, the right blood flows around the body. And we use sensors for that. We use pressure and flow sensors. And obviously a bunch of other examples as well. And then clinically you would use that as well to make sure that it's working well. So sensors give us information about a patient's condition, which can be used to optimize their treatment based on evidence. There's a really wide range of classifications that we can apply to sensors based on the quantity to be measured. So this can apply for electrical signals. There's some examples up on the screen here. For instance, we have ECG pads here, we have pressure sensors here, we have old smartwatches. We have biological sensors here, X-rays here, temperature here. We also can have mechanical, optical, the biochemical, acoustic as well, for instance, a stethoscope, biological, magnetic, thermal, and so on. So there's a lot of different classifications for them. But what physical inputs can be detected using a sensor? So for the next 3 minutes or so, I just want you to talk to the person next to you in groups of 2 or 3 about some physical inputs that we might be able to put under some of these categories here. Now these aren't, for instance, if we go for acoustic, I don't want you to say a stethoscope, or electrical, I don't want you to say an ECG. I want you to talk about what actual parameters of electrical signals can we record. You know, things like voltage, current, impedance for electrical. There's some examples. So have a think about the physical characteristics that you might be able to measure under these categories. Write down a list and then we'll have a quick discussion in 3 minutes. Maybe the 2 of you can discuss some of this. You guys might even be able to all work together or with the person behind you or something like that on this. Are you guys thinking of some examples?
What's the difference between biological and chemical?
So think about cell counts and
Cells.
yeah,
Oh.
yeah.
Then vibration for last lecture I have just flashed
I don't know what this means.
We'll go through this today in the workshop, or tomorrow, today or tomorrow in the workshop.
Oh, the same.
Yeah.
I see this.
Yeah, that will be covered in the workshop. Yeah. Okay, everyone had to think about some options. So, this group here, guys, can you suggest a few options for? So put it up. All right, if everyone could be quiet for a little bit, we're going to have a little discussion about this.
The type of
Okay, everyone, 3 minutes is up. Let's have a chat. So we have some people up the back here that are going to suggest a few ideas. Yep, should be good.
for the electrical, we can we can get the value of the current and the voltage.
Yep. Okay, so we have current and voltage for electrical. Can anyone think of some biological signals that we might be able to get? Sorry? Yes, yes. So these could be particularly insulin. So if we're looking at some biological chemicals that might be inside the body, yes, absolutely. Any other inputs here? Sorry?
Hormones, like hormone levels.
Yes, exactly. Hormone levels. So this would be a biological thing that we could measure. Yep. Sorry?
Skin condition.
So skin conditions. So this would be another biological thing, looking at chemicals on the skin.
So that's not chemical?
It could be chemical, it could be biological. I mean, there's chemicals within the body, so it could be either. Any other inputs? Sorry? Adrenaline? Oh, adrenaline. Okay, yes, yes. So again, this would be a biological thing. But I mean, there was a very good point here that some of the biological and some of the chemical can also be the same. So some examples that I've put on the screen here. So these are not comprehensive. This is just a list of some of the things that we might be able to detect. So acoustic, if we're thinking about wave amplitude, phase, polarization, the spectrum and velocity of the sound signal as well. Biological, we have concentrations. That was something that was brought up a lot, concentrations of different things. The presence of antibodies, microorganisms, someone brought up a response similar to that up the top there, and also biological species. Chemical, so again, your point before was quite good, that the chemical and the biological can overlap. We can also look at chemical concentrations as well, and the presence of different chemical species. Electrical is a fairly easier one to understand. So we've got charge, voltage, current, electric field parameters, conductivity, permittivity, impedance as well could be in there. Magnetic, so you could have magnetic field parameters and polarization. Optical is something that we didn't really think about a lot. So refractive index, reflectivity, absorption, fluorescence, intensity and polarization. Thermal, someone mentioned before, temperature, so that's a common one, flux, specific heat, thermal conductivity. And then mechanical is a very, very common one as well that I don't think we really discussed too much then. So we're talking about position, velocity, acceleration, force, strain, stress, pressure and torque. So the reason I brought this up and the reason I wanted you all to start thinking about this is because your project it should be started by now. And you need to look at a clinical problem. Now, within that clinical problem, you're going to have to come up with a few physical inputs to measure the clinical problem, whether it's a displacement of a device or something like this. All of the clinical problems have a physical thing that has to be measured. So this is exactly where you need to start. You need to start with what is the physical property that we need to measure to resolve this problem. Once you have the physical property, you can then start looking at what sensors can be applied. Okay, so rather than just starting with the sensor, there's a step in between that you can address. So we have some factors that we need to consider in biomedical sensing. So the presence of the sensor must not affect the variable being measured. So this is where we have to consider the interaction between the sensor and the biological system. And on the other side of that coin, the biological system must not affect the performance of the sensor. So the foreign body reaction to an implanted sensor may prevent its operation or have a problem with that. This is particularly important for long-term sensors. I don't know if any of you are aware of the properties of tissue integration into medical devices, but there's sort of essentially two ways to look at this. Some medical devices, you really want tissue integration because it helps a device become part of the body. Some artificial hips are a very good example. For those of you that have ever seen an artificial hip, you'll see that some of them have a very rough metallic surface on them. And what this does is when it's implanted, the bone tissue essentially grows into that rough metallic surface, grips onto it and helps it hold there. There's other artificial hips that don't have that they can argue are better. But tissue integration is a very important thing to think about when you're designing your sensor. Do you want it or do you want to prevent it? So some sensors might even want to measure tissue integration, but the majority of them don't. The majority of them, you don't want any tissue to grow into there because otherwise that's going to affect the performance of the sensor. You can even see on the screen here, this is some results from one of my research labs where we were developing basically a micro 3D printed scaffold to encourage tissue to grow onto it. And within 14 days, we had complete cell growth within that scaffold. So we were trying to encourage it, and that's why it happened so quickly, and it worked really well. But if you have a sensor that's implanted in the body and after 14 days it's covered in tissue, it's probably not going to work. Because a lot of sensors rely on having basically a free barrier between the sensor and what they're measuring. For instance, if you think of blood pressure sensors, they typically work on strain, and they might have a small barrier in there that essentially moves, and that's how they detect strain. If that barrier were to have tissue growing into it, it wouldn't deform the same, so it wouldn't measure the pressure very well at all, or it might even become completely occluded. So these are very important things to think about when designing a sensor. Other things to think about are the sensor must be stable. So you don't really want any drift or loss of sensitivity. And we'll talk about both drift and sensitivity later on in this lecture. And you want it to be stable within its adequate lifetime as well. So your sensor, you will design it to have a lifetime, and it needs to be stable during that time. It's very important that you can do that. For sensors that are only implanted short term, it's not such a huge issue that you have to worry about. But long-term implantable sensors need to be quite reliable. And packaging can be a key element of this. It also needs to be considered in the design, fabrication and use of the device. So a really good example is a very commonly used clinical sensor. It's called a pulmonary artery or Swan-Ganz catheter. It's inserted into one of your blood vessels. This yellow part here is inserted into one of the blood vessels. And basically it measures the blood flow around the body. I'll explain how it works a lot more in a lecture in 2 weeks when we're looking at practical applications. But for now, if you have a look at the way the packaging is designed, it's not just a flat container with everything just folded in. It's designed particularly well to hold everything in place so it's not damaged during transit. It doesn't have any drift or error properties when it arrives. So this is very important. And now we're going to be talking about performance characteristics of sensors. So this is going to use the majority of our lecture up today, but it's very important for everyone to get an understanding of these characteristics for when they're picking their sensors, particularly for their project, or imaging techniques, but it applies to both. So first of all, the transfer function of a sensor. So a transfer function essentially provides the relationship between the physical property and the usable output signal. Okay, so in this case, we just have a basic linear trace here where this is a pressure sensor. As the pressure increases in whatever vessel it's measuring, the output voltage of the sensor increases linearly. Very, very simple version of this, but why is this so important? Can anyone think of any ideas of why we need this? Blood pressure, yes. So, I mean, there's a load of different applications for this kind of thing, but why a transfer function? Why do we need to know this for all of our sensors? Sorry? Yeah, so it gives us our data. So you're exactly right. Earlier when we talked about what a sensor is, it's something that provides a usable output. Now, this transfer function is what gives us our usable output. So if we just measure the pressure but we don't have any transfer function, we don't have any output. So that's essentially what it gives us. So this is an example where you said a blood pressure before. This is an example of a pressure sensor, exactly why we need it. So let's say you have a pressure vessel here. It doesn't necessarily need to be a man-made thing. It can be the pressure in your artery or your veins as well. We then have a pressure sensor that measures it. We typically have an amplifier as well, where you're essentially powering it, and the voltage that comes out of the pressure sensor goes through this amplifier. It then typically goes through a data acquisition system. So a data acquisition system, all it really is something that records the voltage or the current change of the sensor, or whatever parameter that is, and converts that to a usable value. Okay? So basically within your data acquisition, you then apply a gain and an offset, which gives you this line. So if you think about this line, this is a straight line, so we can just apply y equals mx plus c, where c is the y-intercept. The offset would be the y-intercept. The gain is just the slope of the line. Very, very simple. And then you apply this transfer function, and then you can get it back to a pressure to display on your screen, on your clinical monitor, whatever it is. So this is an example of where that is very useful. So if we have two different sensors, let's say we start with the sensor on the left in our whatever we're doing. Let's say we're testing a new medical device. Now we've put in in this case, a pressure sensor. We know the transfer function of that sensor. It's working fine. We then discover that the sensor's broken and we need to replace it. And we replace it with the one on the right there. Can anyone tell me what we would do to the transfer function to get this new signal in that's quite accurate? Any thoughts? Sorry?
You'd have to change the gain and offset values.
Yes.
So the second one has less gain.
So what would you do to the offset value?
The offset value looks approximately the same to me, maybe just a little bit higher.
You're exactly right. The only reason it's a little bit higher is because of my poor drawing in PowerPoint. So in this case, you would adjust the gain value for the transfer function. So in this case, you would decrease the gain because the slope of the line is decreased. Quite easy, right? So then let's look at another case. Would you like to take this question again, or should we let's open it up to someone else, because you already know the answer. Yeah. Any thoughts on what we would do?
We'd change the offset and increase it for the second sensor.
And what would you do with the gain?
We would leave it the same.
Exactly. My drawing in PowerPoint was okay this time. You could see that the gain was consistent, and in this case we would just decrease the offset of the sensor. So this is a fairly easy application. Now what would you do?
You'd probably most likely have to change your function completely. So your gain and offset, you'd have to add another factor just because it's no longer a linear relationship.
Exactly. Very good answer. So in this case, we are going to have to increase the offset because we have, it's obviously increased here. And then we're going to have to apply a non-linear gain. So there's a lot of sensors out there that aren't linear. It can be rare sometimes to find a good sensor that is linear. A lot of them require a non-linear gain, and this is very, very important when we're thinking about calibration of our sensors as well. So then if we go down to this is another important characteristic of our sensors, calibration. We need to make sure that they are reading the correct values. So the calibration of your sensor is vital to ensure that the output is correct. And the same sensor model may have a different calibration and thus a different transfer function. So in my laboratory, for instance, at the hospital, we measure pressure a lot. We always have to do this because we're trying to build new artificial hearts that have to keep blood pressure up. One of the things that we do is we have probably about 12 pressure sensors, all in a large mechanical system that represents your heart and your circulatory system. It's called a mock circulation loop. Think of it as an artificial heart and circulatory system. It sits on the bench. It beats away just like your normal heart does. And so we need to measure pressures all over this system. If we were to just buy a whole bunch of pressure sensors, plug them in, and just assume that they're all calibrated the same, our results would be way off because they are not always the same. So it's important when you are using a sensor in these sort of applications that you calibrate each sensor individually and work out their transfer function individually. And in this case, it's quite easy. We can do, if we know that it is a linear transfer function, if that's something that we happen to be aware of, then we can simply do a 2-point calibration test. So we basically just need to have a known value of something and then use 2 different points within the range of the sensor. So for instance, if we were measuring pressure, one way that we might be able to calibrate that is with a height of fluid. We know that this is a mechanical property that won't really change. Pressure of a vertical tank here equals rho GH. So we can put a pressure sensor at the bottom here and then fill up the tank until we get a certain pressure, measure the voltage at each point, and then use that for the calibration of the sensor. Okay, so that's quite easy. In the other case where we had the nonlinear gain, obviously we can't just apply a 2-point calibration method in this case. So it's very important to consider how we might be able to calibrate it. Because if we did that, we would just get this straight line here, and we would have quite a bit of inaccuracy, particularly at the middle here, which we'll talk about a little bit later as well. So to overcome that, it's fairly simple. We do at least a 3-point calibration curve where we can then apply a function to it. So in this case, you would take at least 3 points within the range of the sensor, measure the pressure, measure the voltage. You should know the pressure because it's a mechanical thing that you've actually calculated here that shouldn't change. As long as the density of the fluid is known and gravity and height are known, then it's quite easy. You can also apply much more than 3 points as well. Particularly, it's useful for some sensors that have a variety of different calibration curves. So that's something to keep in mind. Response time of the sensor is something else to keep in mind here. We won't go into this in a huge amount of detail. The maths behind it is a little bit beyond the scope of what this unit covers, but essentially the response time indicates the time it takes for a sensor to reach a certain percent of its final steady state value when the input is changed. So for instance, we see here if the input goes along, our sensor is measuring that quite nice. The input has a sudden step change. Then we have 2 different response times here of the sensors, the red line and the blue line here. So the red line here, we could say it is potentially overdamped because it takes a very long time to get to that input line and you don't really get any overshoot. And in the case of the blue line here, we could say it's underdamped because it overshoots and then undershoots, overshoots, undershoots until it eventually gets there. There's a bunch of different ways to measure response time, and you can look these up in the text as well, but it's a little bit beyond the scope here. Linearity is something that we discussed before when we were talking about nonlinear gains and also calibration. So sometimes we can assume a sensor to be linear even if it is a little bit nonlinear, depending on the accuracy that you require. So linearity essentially measures the maximum deviation from the reading from a straight calibration line or from whatever calibration line you may have applied, generally straight. And then it's normally expressed as a percentage of the actual reading or the full-scale reading. So if we look on the left here, we have an ideal curve. This dotted line might be our transfer function, for instance. And then the actual measured curve here is our red line. Depending on what kind of accuracy we need from the sensor, some of these you might still be within 2% or something like that, which might be perfectly reasonable in a medical application. In fact, most sensors are much worse than 2% accuracy in medical applications. So that might be perfectly fine. But then if we look at the case on the right here, obviously our measured curve and our ideal curve are quite far off. And in this case, we would need to apply a nonlinear gain and use at least a 3-point calibration method. So moving on to sensitivity. So sensitivity is the ratio between a change in the physical parameter to measure and the usable output. It's defined as the derivative of the output in respect to the input or the smallest fractional change a sensor can measure. So, which one of these has a higher sensitivity? Everyone agrees it's the blue one. So sensitivity is really dealing with the slope of the transfer function that we spoke about earlier. It's very, very simple. But you can have sensitivity error. Okay, so this is, in this case, it shows it quite nicely on the right here. Sensitivity error is essentially a departure from the original transfer function. It's very important to know what that error is of your sensors, and also for which ranges that error applies. So in this case, we have an ideal curve going through here, and then we have a sensitivity error going along here. In this case, we can see that there is no offset error. They are connected at the 0, 0 point, and so it's only sensitivity error, but you can also have error in your offset as well. Again, it is so important to know the error of your sensors, because a lot of people will draw conclusions based on what they've measured. Say they noticed a 2% or a 3% increase in blood pressure with a particular medication. If your sensor's error is within 2 or 3% within that range, then you haven't actually noticed anything. So that's where it's really critical to know the error of your sensor, and again, with the offset as well. So offset we've pretty much covered, so it refers to the output value when the input is 0. And in this case, you can see that the offset here is it's actually quite close to 0, but we already covered that before. Drift. So drift is another key parameter when dealing with sensors, particularly for implantable sensors. Non-implantable sensors, it's not always an issue if the drift only occurs within the body. So it essentially refers to the change in the sensor reading when the input remains constant. And it can be quantified by running multiple calibration tests over time and determining the corresponding changes in the intercept and the slope of the calibration line. So this input-output relationship may change over time, but it may also be dependent on other variables. So it's not just necessarily time that can influence drift. It could be, for instance, something growing into the sensor or environmental changes and things like that. So in this case, there's sensitivity drift and offset drift. You can see examples from them on the screen here. So sensitivity drift, it drifts only in its slope of its line. Offset, it can drift up and down. You can also, of course, have both in sensors. So it's quite a challenge to overcome this with some devices. We have implantable devices and non-implantable devices. Non-implantable devices, it can be a little bit easier because, as we showed before, you can calibrate a sensor. So we can simply, if we notice some drift, we can take a real value and we can recalibrate it. Not so useful if you're about to put this into a patient. You probably don't have time to be sitting there calibrating a sensor. But particularly bad if it's inside a patient. So can anyone think of ways that we might be able to overcome issues like this? Actually, let's take a few minutes to discuss that. And then I'll walk around the room and pick on someone again. So 3 minutes to chat about how we might be able to overcome sensor drift. you two might even be able to discuss it together if you like. Okay. Thanks, everyone. So I will choose this group. Anyone want to give me an idea of what they came up with?
All right. You thought of having a feedback loop so that it constantly senses how much drift is there and compensate for it.
So how would you sense how much drift is there?
Based on the old readings and compare it with the new ones.
And what if the thing that you're measuring has changed? So the old readings no longer apply?
Old readings.
So there's a different thing you're reading?
Yeah.
So it's a
different...
All right, we're not screwed. We're okay. But very good thoughts there. Anyone else have some ideas on what we might be able to do? Anyone in the middle here?
Like you essentially just need to give it a defined input and then check what the output is. So.
Yep. So calibration in real time in the body.
Yeah.
Yeah. So that's definitely one way that we can overcome that.
Could you also have two sensors that are measuring the same thing and then just contrast what the two values are?
Exactly. So you can also have redundancy in your sensors built in. So that's the two very, very good ideas. So definitely calibration in the body, which is not always easy. It really depends on the sensor. Any other ideas from the audience? Sorry? Okay. Okay, so another idea that we might be able to do that we discussed up the back as well. Oh, sorry?
The frequency of the drift may be different with the...
Hold on, I'll give you this so everyone can hear.
The frequency of the drift may be different with the frequency of the signal. So can build up a filter out the drift, only leave the specific frequency of the signal. So
using signal conditioning essentially to overcome the problem.
Yeah, software.
Yep, absolutely. And another thing you might be able to do is if you can define the drift before you implant the sensor, then you might also be able to use a time-varying transfer function. So we talked about nonlinear transfer functions before, but you could also potentially use time-varying transfer functions. So, for instance, this would only be if it's something consistent. If you know the drift, it's very well characterized, something that you can really define. Okay? Yep.
To find out that time-sensitive transfer function, you have to calibrate it over time.
Exactly.
And then apply that.
Yes. Yes. And you would have to hope that all of the sensors are fairly consistent with their drift. It's not always something that we can overcome either. If we look at implantable, long-term implantable pressure sensors, they do exist. There is something called the CardioMEMS pressure sensor, but it has drift as well. So it's very difficult to overcome that. And one of the things I work on is artificial hearts and how we can control them. So to control these artificial hearts, there's a real need for that, because if you wake up in the morning and your heart rate changes and then you go for a jog and then you come to university, your heart rate changes the whole time. The contractility of your heart changes all the time. You might only be pumping 3 or 4 litres a minute while you're asleep, whereas while you're exercising, you might be pumping 20 litres a minute out of your heart. The problem with the artificial hearts that we have at the moment is that they don't change. The clinician, the doctor, sets a speed for the pump, and that's what you get. So you go home with 5 litres a minute pumping out of your heart, and if you try to exercise, you still have about 5 litres a minute pumping out, which really limits your exercise capacity. It limits your quality of life. Apparently, it even gives you bad dreams if you're pumping slightly too fast during sleep. So that was something I didn't know before. And so we need a way of measuring what the patient is doing and then automatically changing the performance of the device to match that. So that's when I was talking about control systems earlier on in this lecture. That's one way that we can potentially overcome this problem. But sensor drift is a massive issue for us because long-term implantable pressure sensors don't really exist. They typically have something that, like a membrane that will detect the pressure, that will deform and then detect the pressure. And this membrane, it can have tissue grow onto it, which is a really big problem. If you have tissue growing onto a membrane, it changes the deformability of the membrane and then leads to drift of the sensor. And also you can have other issues that lead to drift. So that's something that we're currently working on. We're working on devices that are non-drift, or at least very, very low drift. But then we also brought up calibration, which is another thing that can possibly be done. It's very hard when you're dealing with long-term implantable blood pressure sensors because calibration means usually putting a wire and a tube inside the patient's heart and vessels, which is not always so easy. So, for now, we have a bit to discuss as well. I think the lecture will finish slightly early today, but we might have a 10-minute break or so now, and then come back here at about just before 3 o'clock, and then we'll continue. So it was a time-dependent. I don't have it actually. So a time-dependent change in the transfer function. So, for instance, what we can do. Are you talking about the real-time calibration for drift or the time-varying drift? The time-varying calibration.
So the answer to this question, somebody's interested in monitoring transfer rate.
Yep. So this basically means putting a sensor into the patient. And then working out what the real value is. So having, for instance, let's say we're measuring blood pressure in the patient using the implanted sensor. What we can do is, if we think it's drifted a little bit, we can take another sensor outside the body, calibrate it, insert that into the body, and then see how different they are, and then adjust the transfer function. Just one, as long as it's one sensor that we know is accurate, then we put it into the body quickly. We measure the say pressure, the blood pressure, and then we can adjust the transfer function of the implantable sensor to match the one that we've just put in. And then we take that other one out because we know that other one's calibrated. So it's a real-time calibration. If you can get a known, a calibrated pressure sensor into the same location short term, then you can use that to calibrate the sensor that's already there. Yeah, but then you've also got time varying as well. So over a very long period of time. Yeah. Sweet.
just wanted to ask that this slide seems quite different to others of yours.
They are. They'll be uploaded. Yeah, I just didn't want to give the answers away so that everyone can just shout them out. So yeah, don't worry. I'll mention that actually when we get started. Good point. Thank you. All right. Thanks, everyone. All right, we'll move on with the lecture now. So we'll go over a few more important performance characteristics, and then we'll just run through a couple of exercises, and then do a summary for the upcoming weeks as well. So the next performance characteristic to talk about is range. Okay, so range, essentially we're looking at the range of the physical parameter to measure that can be converted to the usable output form by the sensor. Usually outside the range of the signal is non-accurate. A lot of the times they can at least detect a signal outside that range, but a range is usually specified based on the accuracy of the sensor. So some examples of this include some flow sensors that I work with. Low flow rates are not within the specified range because they have an error of about 10%. Flow rates between, say, 2 to 10 litres per minute are quite good. They're calibrated nicely and only have about a 2% or 3% error in that range. And then obviously upper limits, you then get more error. So who can tell me which one of these has the biggest range, the green, blue or red? Exactly. Trick question. I should stop trying to do those. So we have exactly the same range because we're not looking at anything along here. We're looking at basically the endpoints here. Very, very basic. So the range of all of these is the same, and of course the transfer functions would be quite different. So hysteresis is another characteristic that we'll talk about. So some sensors exhibit a non-linear trend depending if the input is increasing or decreasing. This is surprisingly common in sensors, and we need to account for that when we're dealing with our calibrations. So this essentially means that the sensor has two different transfer functions depending on the input direction. So in this case, I don't know if you can see the arrows very well, but they are moving this way as the, in this case, say pressure goes up, and then this way as the pressure goes down. Now, just on a little side note, someone reminded me earlier that the slides are a little bit different to the ones that are on the Moodle. Yes, they are. I'll be uploading these slides either today or tomorrow. I just didn't want to give you all of the answers to what I wanted you to talk about. Otherwise, you would just say exactly what was already on the slides. So if we think about hysteresis, how might we be able to overcome this? Can anyone think of some ideas? So it is a real problem, and there are ways to overcome it. Sample 2 points.
So, like, your current value of the previous value is in which direction?
Yeah, so, I mean, we would have two different transfer functions. You are correct. So rather than sampling 2 points, what we might be able to do is take the derivative. So we know the direction it's going, essentially. Work out the direction it's going, and then apply the correct transfer function. Okay, so this would just come down to the history of the sensor. So that's usually a fairly easy thing to overcome as long as you know what those two functions are. Then we've got accuracy and precision. So we should be aware of these. Accuracy is how close the measurements are to the true value. So in the case of the top hitting the bullseye, it's represented as the difference between the true value and the value that's measured by the sensor. And the true value should be traceable to a reference, so in this case, a bullseye. Precision, how reproducible are the measurements? So we'll talk about reproducibility soon as well. And multiple measurements may give very similar values, but it doesn't mean that they are accurate. So then if we look at these cases, so we have on the top left here, we have a bunch of, let's pretend this is still a dartboard and the red dots are where the darts have hit. So we can see in the top left that the darts are not really that close to each other, and they're certainly not very close to the bullseye. So this is about my skill level when playing darts. I'm not precise and I'm not accurate. Then we have people that are precise but not accurate, so where they're grouped together but they're not really that close to where it needs to be. And the same thing with sensors. We can have accurate but not precise, and then of course precise and accurate where they are all near where they need to be. and they're close together. Reproducibility is another important thing to consider. We won't go into it a huge amount today. Again, it's probably a little bit beyond the scope of what we're doing. But it essentially describes how close the measurements are when the same input is measured repeatedly over time. So reproducibility should be able to include human factors as well in it. Repeatability doesn't, or doesn't include multiple users. So it's represented by a range of values around a measurement related to the standard deviation of the measurement. So reproducibility may also change at different ranges in the sensor as well. It's like everything that we've spoken about today. It can change, it can be non-linear. So in this case, we can see that it's not so good at low concentrations of whatever this sensor is measuring, whereas it's quite good at high concentrations.
For reproducibility, is that one sensor over like a whole data set, or is that using the same kind of sensor for different data sets?
I mean, you could apply it to both. You could also talk about reproducibility of a model of a sensor as well and have a series of sensors. So the reproducibility doesn't necessarily have to be confined to just one thing. So when we're looking at reproducibility, we do have experimental errors in them as well. These are typically defined as random or systematic errors. In the case of random errors, that you can often get noise on your experimental startup or errors to do with your experimental startup. You can get a change of the experimental conditions. For instance, let's say we were measuring the air pressure inside this room during the lecture. Obviously, as the doors open and close, we have environmental changes that are going to change our sensor readings, and they're going to be kind of random errors. We can also have random operator errors. And the way we deal with them is just generally statistics. So if you take enough readings from enough sensors, you can look at the standard deviation over multiple measurements and hopefully get something that's statistically significant. We can also have systematic errors, which are instrumental, physical, and human limitations, such as non-calibrated instruments. An experimental method always renders higher or lower values than the true ones. How to deal with them is careful calibration of your sensors and also your experimental setup. And applying the best possible techniques and methods. So this includes developing SOPs, trying to do exactly the same thing again, using a lot of training, things like that. That's how you really overcome reproducibility issues. If we look at, so the next couple of slides are going to talk about two different sensor characteristics at once, both resolution and noise, but they can be quite related, which is why they're both covered in the next couple of slides together. So if we think about resolution, it's essentially the like a small value of change that can be reliably measured by the sensor. So for instance, if it's pressure, it might be, say, 1 millipascal or something like that. So it's really the smallest distinguishable input change that can be detected with certainty. So it's important to think about that, the last couple of words there, with certainty as well. So if we look at the results on the screen here, we can see that there's no noise in the sensor. So whatever, in this case, we're measuring a voltage against time, and we've increased the concentration of some kind of chemical. So it's detecting a concentration of a chemical over time. We can see that there's almost no noise. These are basically flat lines, very nice step input changes as the input to the sensor has changed. And we can really distinguish in 0.1 millimolar increments. Right? So our resolution there is very, very good. It's probably 0.1 millimolar in this case. If we then add noise to a signal, and it's important to keep in mind that pretty much all sensors have some form of noise, we can see that all of a sudden our resolution gets worse. So a lot of sensors have, it's very, very common. It can be due to manufacturing issues, it can be due to your experimental setup issues, it can be due to just knocking the sensor, experimental error, all these kind of things. But most sensors will have some form of noise. And this is a perfect example of a bit of noise. You can see now that when the increment has changed to 0.1 millimolar from 0, you can't actually distinguish that anymore. So noise has essentially dropped the resolution of the sensor. So our resolution now, we might be able to say, is 0.5 millimolar. We can actually still reliably detect that, and as we go up, we can see that we can still detect these. Whereas in the case of quite severe noise, we're not even really able to detect a 2 millimolar change here. We might be able to say the resolution here is 5 millimolar. Okay? So overcoming noise can be a problem. My way of overcoming it experimentally is just to spend more money on a better sensor. But I actually don't know how you would overcome this with actually building your sensor, other than making it more reliable. So we're going to go through some performance characteristics examples, just to quickly summarize some of the things that we've learnt. So the first one I'll put up on the screen what the solution is, and then the second one will get you guys to spend about 10 to 15 minutes trying to resolve yourself. So for the following sensor example, calculate the transfer function, range, and sensitivity. So in this case, we've already got, we've basically got a concentration of glucose that's being measured by some kind of biological or chemical sensor. And then we've got an output voltage from that that's going to our data acquisition system. And in this case, as the concentration has gone up, our voltage has obviously gone up as well. It's already been mapped for us. So we've already got, essentially we could draw the transfer function on here if we want. It's just going to be a straight line through here. So that's quite easy. So in this case, basically the solution is up there, but a brief explanation of that. So if we're looking at the transfer function, it's just a linear equation. In this case, we can see that's quite clear. We can use, I put y equals mx plus b just because I didn't want to confuse the c from concentration of glucose using y equals mx plus c. So in this case, we would express the y value is the voltage of the sensor, and x is the concentration of the glucose, because that's how we've been presented with the data. But it's also important to note in this case that you could present an inverse transfer function. So in the case of with our data acquisition systems, if we were to use this sensor, it reads a concentration of glucose and then it gives us a voltage. We then read that voltage into our data acquisition system and we want to display it on our monitor, what that is. Then we would apply the inverse transfer function there to get that data back to an actual glucose value. Okay? But in this case we won't do that, so it's pretty easy. We calculate the slope. We know what the change of y over the change in x is, so we can work out our transfer function. It's fairly simple. The voltage equals 0.098 of the glucose concentration. In this case, our sensitivity is really just the slope of the line here, so 0.09. In this case, we're going to put units on it, millimolars per millivolt. So that's the sensitivity of the sensor. The range we've already been presented with here, in this case, it's between 0 and 5. We don't know anything beyond that, so we can't really do anything beyond that. So in this case, it was quite easy. I want you to now work on example 2. For the next 10 to 15 minutes, please feel free to work on that with the people next to you. So in this case, we're working on a new temperature sensor with the readings in the table. Hopefully you can all read them. If not, this should be in your notes. Plot the input and output calibration for this sensor. Find the offset and sensitivity between 0 and 70, and then the sensitivity between 70 and 100.
This is like a trick question.
Sorry?
This is like a trick question.
We don't have tutes.
Oh no. I mean like the lab session, like the workshop.
So the workshops are actually going to be working on your projects. Yeah. We won't actually be covering things like this in the workshop.
I get that. But it's like sort of like an admin question. It's like if I have a workshop tomorrow, can I attend the one today?
Oh, sorry. No, because they're overbooked. The one today is overbooked.
Oh, really?
So it's important to stay in your workshop that you have. Yeah.
So like
try to.
way around that, even if like my group members are like already in like today's workshop. I'm like the only one that's not in today's workshop.
Oh, so you already have your group?
Yeah.
Okay. I think it's probably okay if the numbers are small to swap. Yeah, email myself and Steve. and it should be okay. Come along today. I'm taking the workshop today. If we can't fit you in, then...
Cool. So...
So I'll give everyone until 3:25 to get this solved. And also just a note that the workshops will be covering the project work, so we can't cover problems like this in the workshop. But keep in mind all lecture materials will be examinable, so things like this are very important to know how to do. Okay, has everyone got the solution for that? And compared it probably with the people next to you to make sure everyone's correct? So when I was walking around the room, I noticed some people were doing this by hand. Other people, very clever, had worked out you can easily do it in Excel. The problem for the people that did it that way, you may not have access to that during your exam, so doing things by hand might not be bad practice for this. So of course we can do it in Excel. So in this case, for those that didn't do it, we can copy them in. Now we're after between, first of all, to plot the transfer function, or the data, sorry. So you can see that we can easily do that. And even looking at, it's not on the screen, is it? Okay, that's interesting. All right. All right, for some reason that's not working on my screen, so we'll just go to straight to the solution. But plotting it in Excel was definitely one way to do it, and you can see straight away that it's not really a linear function, and that's why we asked you to plot what you think or determine the transfer function between the different points there. So essentially we can plot it as you can see there. We can see it's relatively linear between 0 and 70. The transfer function was 0.84. The voltage equals 0.84 times the temperature plus 10.875. So in this case, we know the offset is just negative 10.875 millivolts in this case, and the sensitivity here would be 0.84 degrees Celsius per millivolt. And that's between 0 and 70. And then if we go to the next region, where again we can see that it's quite different to that first region, and this is not unusual for a sensor, keep in mind. So our transfer function, our gain was significantly lower, we can see, because the slope of the line was a lot lower. Here we can see it's 0.173 plus 56.12. The sensitivity is 0.173 degrees Celsius per millivolt. Yes? I did have it on Excel. Because the y-intercept was about... Do you mean for the first one? Yeah. The y-intercept is about 10.
Oh, so you did it off the Excel line?
Yes.
If you were doing it by hand, though, would you say that the offset was 0.3?
You're close. What points did you use?
If I just use the first point and the 17 point to make the line.
Yeah, that should have given you the same answer. Let me see if I can get it up on here. Not quite. Let me see if I can get it up. Yeah. So, laptop. Okay, so sorry? Okay, so let's have a look at how we got this result. So the easiest way to calculate the slope of the line in this case is we're just going to use XL. So we're going to go between 0 and 70. Sorry. So we've plotted it between 0 and 70 now. You can see that's fairly linear. We can add a trend line. We're assuming it's linear, and we're going to display the equation on the chart. So this is how I came to that conclusion with that one. Now please do tell me if you disagree, that's fine. As all lecturers, I'm allowed to be wrong, I'm just not allowed to mislead you. So of course you won't have access to this in the lecture.
Doing it by hand though, which points would you pick to figure out the trend line?
So
The first point and the last point, which gave you quite a different offset value.
actually that is a very good point, because this trend line doesn't go through that. Yeah. So
Slightly different gain value, like
yep.
different 0.79, but
Yep.
the offset value was 12.3.
No, you make an excellent point. Okay, so for those of you that were listening to that, obviously doing it through Excel is going to give us a trend line through the middle of all of those points, and that's going to give us it's going to be probably a more statistical way of doing it. But if you were doing that by hand, obviously that's going to be very challenging, as you say. So in your case, you have, can you tell me what your gain and offset were?
Yeah, so my gain was 0.793 and I had an offset of 12.3.
So that was, okay, so we can see obviously in that case that we are very, very close to the final answer. And you're exactly right. So the way you've done that by hand, taking the first and last point in that case, is a good approximation. If we were going to do this in the real world situation, obviously having access to these tools, we wouldn't take the first and last point, but in the exam, you would do that. So you are correct, yeah. And if that was the result in the exam, of course you'd be marked correct.
The unit of the sensitivity should be
You are correct. Yeah, that's you are correct. So actually, there is another small mistake on there. I apologise. The sensitivity units are back to front. It should be millivolts per degrees Celsius.
Can I ask another question?
Sure.
How come the offset has a negative in front of it?
Okay. Yes, that is.
Okay, cool.
All right, let's fix the slides up so at least they can be uploaded correctly. Okay. Thank you very much for picking that up. Okay, so if we're all happy with that, and of course the values for those that did this by hand will also be different as well. And I'll need to change that sensitivity unit as well, sorry?
That one was really similar to the by hand.
Oh, okay, great. Okay, so in this case, looking back on what we've learned, how would we address this in the real world? So how would we address these two different sensitivities and gains of these two functions, or essentially having to apply two functions to one sensor? Any thoughts? Yep.
Could you specify that its range only goes up to 70 degrees Celsius if that's like an acceptable measurement range?
Yes, absolutely.
Say after that it's error.
Yep. Particularly, I mean, there's a few ways we could do this. One, we could apply a nonlinear gain. as well, so that way then we cover that area. The other thing is we can have two distinct regions where, for instance, between a certain temperature it applies one gain and offset, and between another temperature it applies the other gain and offset. So we have two functions in it. But as we saw with the second case, that there was a bit of error in that as well. So you would need to decide if the error is too large to be within your range. And if it's too large, then you're exactly right. We would define the range as being between 0 and 70. Okay? So, moving on from that. So that's the majority of the lecture today. So the workshops that are coming up this afternoon after this and also tomorrow, please try to attend the workshop that you've already selected, because we are kind of at capacity, I think, for both rooms. Hopefully the groups that you've picked are in the same workshop as you, because you'll be working in your group projects together during your workshops. That's what the workshop time will be used for. Week 2, which is this week, we'll use that time to focus on stage 1 of your project, which we will go through a few slides at the start of the workshop as well to explain that in more detail. This is the individual stage. And your experts, which are the demonstrators, they'll roam around the room to answer any individual questions. In week 3, hopefully you've formed groups by that stage. And then you can use this time to plan for stage 2. If everyone up the back can just keep it down for a little bit, we're not quite finished yet. Thank you. So week 3, hopefully you form those groups. And keep in mind that the group members can have different clinical problems in stage 1. Okay, so if you've picked a different problem to your group members, you can still form a group and then pick one of those problems to continue on to stage 3 and after that. Or stage 2 and after that, sorry. And then from week 4, your group will be assigned an expert and given a time to meet them. Next week, guys. So next week we will have a really good guest lecture. You're very lucky to have this guy here. I think he's formed something like 13 medical device companies in his life. He's actually taken things from the bench to the bedside, actually translated devices. He's one of the few people I know that has done that on several different occasions and raised just countless amounts of investment funds for these companies. So his name is Professor Uli Steinseifer. He will be giving the guest lecture next week on commercialization of medical devices, or translation of these medical devices, and also a little bit of guidance on how to build a business case and do some market research. This is very important for your projects because you will be expected to do something similar. So make sure you come along and make sure you pay attention. It's going to be very useful for you. And keep in mind that all of this lecture content, including the guest lectures, is examinable. Okay? People always ask what's going to be on the exam. It could cover anything delivered in your lectures. So that is it for today. Thank you very much to everyone, especially those that pointed out the errors on the slides. You have set up your group?
Yes. Should we send an email to you or?
So there will be a way to do it online. So there will be a thing on the Moodle for setting up your group. Okay?
We set up on Moodle.
Yes.
And some of us have tutorial this afternoon, but others can't select this afternoon.
Okay. How many of you are in?
5.
So there's 5, but how many are in today and how many are in tomorrow?
3 in today and 2.
Oh, okay.
Because one person is just choose this unit today.
Are the 3 from today able to swap to tomorrow or vice versa?
Sorry?
Can you swap so you're all in one workshop?
We would like in this afternoon.
You would like to come this afternoon?
Yes.
You can try. So the room is actually slightly overbooked at the moment, so there might not be very much space, but you can try to come this afternoon.
Thank you very much.
So I mean, it's starting in 20 minutes, so come along and see if you can fit in. Okay, thanks. Your group? Yeah, you choose your group. And the topic as well. So basically in stage one, you choose, it's an individual thing, you choose the clinical problem and then you do that by yourself. And then for stage two, you form a group, or you can already start talking to people now and forming a group now. You form a group and then you all work on one clinical problem. So you all maybe vote on what the one problem will be. And then you work on that. Excellent, thanks. Hi.
I noticed you mentioned in this week's workshop we will focus on our stage one.
Yes.
The video project?
Yes.
So which topic?
Sorry?
Which topic?
You choose. So you have this 4 clinical problems online. You should read all 4 of the papers, see which one you like, which one you enjoy, which one you're passionate about, and then work on that one.
Okay.
Yeah. Okay. And then when you come together as a group, you then pick one of those clinical problems, and then you all work on that for the rest of the semester.
Okay.
Okay. It doesn't matter if you all do different ones at the start in stage 1. You work together from stage 2 onwards.
Okay. Thank you very much.
Okay. Thanks.